Yes, so for the next talk, we have the pleasure of having David Ledvinka, who will talk about formalizing probability.
Yes, so I'm going to talk about formalizing Brownian motion in Lean. So this is joint work with Remy, Etienne, Peter, and there's other contributions from Marcus, Jonas, Lorenzo, Alessio, Jeremy, Pietro, and then also help from Sebastian on Zulip. Okay, so the first question to ask is, what is Brownian motion? So Brownian motion, so firstly, is a stochastic process. What this means is that it's a sequence of random variables. And I mean sequence in a generalized sense. So we have some index, which is, in this case, nn real valued. And then for any particular t, we have a random variable, which is a function from some sample space omega to r. And then we say that this stochastic process is a Brownian motion with respect to a measure p if the following two conditions hold. So firstly, if it's almost surely continuous. So what we mean by this is if we take a particular omega and plug it in, we get a sample path, which is just a function from nn real to real. And we can ask if this is a continuous function. And if it is the case that this is continuous for almost all omega with respect to p, then we'll say it's almost everywhere continuous. So this is actually Lean code. So the next condition I wrote in sort of pseudo Lean code. And this basically says that the finite dimensional distributions of Brownian motion should be given by a multivariate normal with mean 0 and covariance given by a matrix defined by, so the ijth entry is equal to the minimum of ti and tj. Okay, and so perhaps the best way to sort of get a sense of what Brownian motion is not to read the definition, but to see it. So I did this simulation of Brownian motion in Lean. Of course, this is just an approximation. It's not actually Brownian motion. And unfortunately, also, it seems like there's not an easy way to plot an array of floats yet in Lean. So I did export the array to Python to do the plotting. It would be nice eventually if we can just plot this in Lean. But so it looks something like this. And you can see from this process here that it is continuous but very erratic. And in fact, one can prove that it's almost surely nowhere differentiable, although we have not done that. So that could be open for future work. Okay, I guess go to the next slide. So what does it mean to formalize Brownian motion, right? So the definition here, right, it's very easy to write this down. If we just mean to state what it means to be a Brownian motion, this, I mean, this wouldn't actually be trivial because we hadn't even defined multivariate normal distributions at the beginning of the project, but it wouldn't be hard. It wouldn't be a big deal. But the non-trivial part is actually to show that there exists some process which satisfies the definition, right? So the vast majority of the project is trying to do this. We also do a little bit of API for Brownian motion at the end and show that it satisfies some of the properties that it should have. But the bulk of the project is dedicated to doing this. And I'm going to talk about the steps that we took to do this. However, it's also worth mentioning that each of these steps has a lot of things that will be useful for other projects. So it's not, all of this stuff is just for the construction and then we throw it out. So the first step I will talk about is we had to build a Gaussian API. And what do I mean by that? So we needed multivariate Gaussians. So regular normals were already in MATLAB, but not multivariate Gaussians. And we need Gaussian measures and Gaussian process in general. And of course, when you define things like this in MATLAB, it doesn't just mean for MATLAB or for your own use. It doesn't just mean you just write down the definitions. You have to write a lot of APIs so that these things are actually useful, right? And that's not always trivial. And the reason we need this, in particular the multivariate Gaussians, is we want to be able to define the finite dimensional distributions of Brownian motion, as I said before. So in particular, this lets us say that, okay, I'm again using a sort of pseudo Lean code here. For any finite set j, t1 to tn of n reals, we can define a measure which is on j index vectors, such that if x is some actual j to r, which has this distribution, so omega j to r, it's a random variable, then viewed as a vector, it has the right distribution, right? So we're basically defining the finite dimensional distributions, but we need to take this and define a stochastic process on all of n real to real, right? So that brings us to the next step, which is the Kolmogorov extension theorem. So this was actually done by Peter and Remy a little bit before the public Brownian motion project. but then it was ended up included as part of the project. Or I guess it's in a separate repo, but it's part of the paper. And we rely on it in order to do the following. So the idea of this is to actually construct our stochastic process on NN real to real. So in particular, it's stated in a much more general way with the actual theorem that is in the project. But in particular, what it lets us do is say that for any, we can define a measure P such that it has the right finite dimensional distributions. In other words, for any fin set J, if we restrict P to J in the reasonable sense, you could make precise, then it equals Pj. So one way to state this informally, and you can make formally, is that if X has law P, right? So this is actually a stochastic process, so a random variable, which you can view as a function from NN real to real, then for any finite set of times, it has the right finite dimensional distribution. So xt1 to xtn is a normal with the right covariance matrix. However, a key point is that this does not guarantee continuity. And in fact, you can prove that the extension theorem just gives you the existence of some process which satisfies these properties, and you can come up with counterexamples of some process which satisfies this property, but is not almost surely continuous. So that's where we need the next step, which is the Kolmogorov extension theorem. And this says that the point of this is that we need to construct a modification x prime of x such that x prime has the property we want. So almost surely it's continuous. And a modification here means that if you fix any t, that almost surely x prime t equals xt. So in particular, this will imply that it has the right finite dimensional distributions as well, but then it also has the other property we need, that it's almost surely continuous. And so the existence here is given by the Kolmogorov-Chentsov theorem. And so for the rest of the talk, I'll mostly focus on this because this is the part that I worked on the most, but maybe I'll first say that both of these other parts of the Gaussian API can be used to do a lot of other things. So for example, we could get a multivariate CLT, which is useful. And Gaussian measures can be used to define more complex things. And then of course, Kolmogorov extension theorem can also be used in general. So if you define some measure on its, so in particular, it can apply to uncountable index sets, right? So if you construct some process by defining its finite dimensional distributions under some technical conditions you need, you can then define a process on the uncountable, possibly uncountable set. Okay, so both of those will be useful for other work. I'm going to talk about the KC theorem. So in particular, we actually didn't do sort of the classical one that you might see in introductory textbook. We did a much more general version, which is actually a recent result. So I think the paper was 2023. I'm not sure if that's when it was on arXiv or accepted. I think it might have been accepted into Journal of Theoretical Probability or something like this. So I'll state that in a moment. But so first I'll go over some conditions. So the assumptions of the theorem are we let T and E be extended pseudometric spaces with metrics dt and de, and we let xt be an e-value stochastic process. So as you can see, I've switched back to regular math, but so in our previous language, we would say that x is from t to omega to e, and we say that x satisfies the Kolmogorov condition for exponents pq with pq greater than 0 if the following two conditions hold. So for any s t in t, we have that xsxt is measurable for the Borel sigma algebra on E cross E. And it's sort of easy to see that this holds in our Brownian motion case. And the second condition we need is this Kolmogorov condition, which says that there exists some constant m, such that for any s and t, we have that the expected value of this distance of xs xt to the p is bounded by m times dt stq. So what if this says intuitively is that if the expected distance between x at time s and x at time t is controlled by the distance of s and t. Now there's a p and a q which tell you precisely how that control happens in an m, but sort of that's the rough idea, right? And one can show that for Brownian motion, so in our case, this holds for 2nn with m equal to 2n minus 1 double factorial for any n. So this requires, so what does showing this require? Well, so this distance here in our case would just be the absolute value of xs minus xt, which we know for our pre-Brownian motion, which was our process before we applied this theorem to get a continuous version. So xs minus xt will be, these will both be Gaussians. So this will just be a difference of Gaussians. So ultimately this amounts to computing the moments of a Gaussian. So that's what basically went into that proof there. And then this we proved this following theorem, which says that suppose that T has bounded. So this is a version of the Chentsov theorem, which is modern from 2023, which says that if we suppose that T is bounded covering number with exponent d greater than 0, and I won't explain what that means, and that xt for T and T satisfies the Kolmogorov condition for exponents pq with q greater than d and p greater than 0, then for any beta in 0 to q minus d over p, there exists a finite constant L such that for any countable set T prime in T, we have that the expected value of this is bounded by L. And so intuitively what this means, you can think of this as like a Holder condition, and that will be sort of made precise after, but this is basically saying, that well, it should look, it's sort of like Holder in expectation with or sorry, not in expectation because we have a sup here, right? So it's basically Holder, but the only difference is that we have T is over a countable set, right? So with some extra conditions, you can then turn this into actually saying that the process X is Holder. So we say that furthermore, if E is complete and T is second countable, then the process X has a modification with Holder continuous pass of exponent B or beta for all beta in 0 to q minus dp. And for Brownian motion, this gives us beta in 0, 1 over 2, just by sort of applying it with what we proved here. So a few things to say about this. So the modern version, I believe the sort of modern thing that this paper does is remove second countability from the space E. And I'm not quite sure, to be honest, how useful that is. It may turn out to be useful, but in general, this is much, much more useful than the sort of very specific version you'll see in some introductory, some introductory textbooks. Well, you'll just prove it for real processes. So all this theory can be applied not only to show that other processes have continuous modifications or Holder modifications, but also a lot of the theory we developed to prove this theorem is actually used in sort of a field of probability that studies just bounding the supremum of stochastic processes. So they don't even necessarily care about, I mean, it could be some discrete process where you don't even care about continuity, but a lot of these sort of techniques that we use to prove this are used in the proof. Okay, so now, see how I'm doing on time? Okay, so for the next part of the talk, so I know Remy has given a talk about this project to a few different places and talked about some of the high-level things that we learned from the project. So I know not everyone in the audience has seen it, but given that many probably have, I wanted to sort of focus on a different aspect than he covered in the talk in terms of lessons learned. And in particular, what I want to discuss is the proof of this was very computation heavy, and it required a lot of computation in EN real. So I want to sort of illustrate that and the problems and maybe potential solutions with an example, right? So the example I'm going to work through is this very ugly lemma right here. And so even though this is one particular example, I think the things I'm going to describe are sort of emblematic of a lot of the different lemmas that were in the proof of this theorem. So obviously this is a very ugly lemma, but if you actually think about it just from an informal perspective or formal informal, it's not so bad because you have this whole part, but this is just so I want to show that this is less than infinity, right? But so the sum is in k, so the k pops up here and the k pops up here. So this is just a constant. This is just a constant. So this should be pretty easy. So what's the idea to prove this? Well, the idea is to apply ratio test, right? So we drop this constant and then we apply ratio test because, so using these conditions, we can show that this is less than 1. So it actually suffices to prove that the limit as n goes to infinity of this whole thing equals 1, right? And I figured that the easiest way to do this, rather than trying to somehow compute this limit directly, would be to show that the numerator is asymptotically equivalent to the denominator, right? Because then you can sort of use an algebraic approach where you sort of pull off the pieces one by one, right? That was sort of the idea, right? Okay. So not so fast. So even getting to this part required a lot of pre-processing. And this is the case with basically any of these complicated ENN real proofs, real proofs. So we have to deal with a bunch of edge cases so that we can apply operations. And we also have to convert to real because, so in this case, the use, so the asymptotics API doesn't work for ENN reals. So I had to convert to use that, but there's also a lot of cases where you want to convert to NN real or real in order to apply some either theory or tactic that only works in those cases. So we have to deal with sort of both of these things. Okay, so one example of this is, and there was a bunch of examples in the proof, but just one is that I have to prove that the max of this thing is not equal to infinity. And to clarify here, Q, G, and P were real valued. They're not ENN reals. But this thing takes its value in ENN real. So I have to show that, and obviously if the denominator is finite, or sorry, is 0, then this will be infinity, right? So in some sense, if you look at this, it's obvious that, well, I guess it's not obvious, but with the assumptions that Q is greater than D, it's obvious that this will not be infinity, but it's, still it didn't seem to be doable, at least at the time, with one tactic, right? So it would be very nice if we can get tactics to the point where you can just do this in one go, as opposed to having to do this because I mean, doing this once is not so bad, but you have to do this many times. Okay, so I did several pre-processing lemmas, not just that one, and then we do reduce it to this, right? So what is the proof of this? So it's given by this long string here, and so one thing you'll notice is that there's a lot here, but also it's very repetitive, right? And I mean, because in some sense this should be obvious, because basically I wrote it like this because I didn't want to write out one long string of this is asymptotically equivalent to the bottom, but we're trying to prove that the top is asymptotically equivalent to the bottom. So that basically amounts to dropping the constants, canceling out the 4D, saying that because the top, or that if we wanted to get rid of the Q basically, right, and then one by one pick off each part. But it turns out a lot of these have extra side conditions, which are basically all trivial, but then you have to provide proofs of them, and there doesn't seem to be automated tactics that can prove it. And one maybe point I'll make here is that I actually gave this to Vasily to see if he could simplify this proof with the compute asymptotic tactic. And I did the pre-processing, so I got it to basically, I don't remember if it was exactly at this point, but I got rid of everything was real valued. I got rid of the ENN reals, and still because there was some casts and stuff, the more pre-processing was needed, right? So, but eventually he did manage to get a simplified proof of this, so it was shorter, but it was not quite as nice as you want it to be. You still had to do a lot of finagling to get it to a point where compute asymptotic could work. And I also feel like there's room. So don't get it wrong. I'm very excited about compute asymptotic. I think it'll be very useful. But I think there's room also for sort of a tends to or asymptotic tactic that is like funprop, which can sort of solve these sort of simple cases where so funprop, for example, can solve measurability things, and usually if it's sort of trivial in the sense that it's like a composition of tagged lemmas, right, in sort of an algebraic or just literally compositional way, then funprop will be able to prove measurability or continuity, whatever. I think you should be able to have a simple tactic that can work in a high level of generality. So maybe it has a much higher scope in terms of can works in Banach spaces or whatever, in proving simple tends to and asymptotic lemmas just by being able to pull off the constants. Because you'll see there's a lot of sort of repetition here. This seems like the kind of thing that something like funprop doesn't quite work, but like funprop could do, where you sort of use a very simple naive algorithm just to solve simple cases, and then you have something like compute asymptotic to be able to handle like the more concrete but more involved cases. Okay, so I'm going to talk a bit more about what I think we need. So improved positivity and finiteness, so that would help a lot. Not just because sometimes you have to deal with cases of proving things are positive and finite, but it helps with other tactics, as I'll explain. So one thing I think could definitely be, so ENN real is very annoying, but one way to get around that is to simply cast to NN real and real and use the automation in these types, right? And I think we can do some work to improve the ability to do this casting, right? So even as I said with compute asymptotic, we want to even if that can work, we want to have automation. It doesn't seem to work out of the box. We want to have automation that can actually reduce it into a case where compute asymptotic can handle, or other tactics, right? So one possibility I think is, so there's these tactics, ENAT to NAT and PNAT to NAT. So I think these could be, generalized to, in one particular case, you can maybe make a more general version, but EN and real to N and real, EN and real to N and real. I took a look at this tactic, and I think you could basically port over exactly the algorithm. Unfortunately, I don't think it would actually be very helpful for this project as is, because it doesn't handle powers, and powers are more complicated because of a few issues. For example, a negative power in NAT, I guess in N and real, a negative power or NAT goes to, I guess this might not even apply in this case, but especially in real to real, it goes to 0, right? Because of junk value, whereas it goes to infinity reasonably when you're in N and real. So that causes a problem, but I think these things are overcomable, because often when it's, either you prove, so one case is you improve positivity, so you show that case doesn't happen. But even if it does happen, often when something's infinity, if it can be infinity, it's actually easy to prove, because then you can use simp or something, and sort of the infinity should, if you're improving inequality, the infinity should sort of absorb everything, and that case should be handled. So you might need some case splitting. Obviously, it's not trivial, but I think that these things can be done. And then another example is, so this sort of is tactics which at least bring EN and real to N and real to be able to, then do more, but also just, finishing tactics. We have powerful finishing tactics for other types, like obviously real, and more recently N and real has had some support. So we need to also bring these to EN and real. I'm not sure if exactly ring and field precisely, but stuff like that is powerful finishing. I understand that, it's not as easy to write these algorithms, but I think with more work we can do it. It's just a silly example. Norm num can't even solve this, but exact question mark can, because this lemma is in the is stated in mathlib. But the fact that norm num can't solve this is a bit silly. So I think Sebastian gave another example that's kind of similar to this, where the exact lemma will not be in mathlib, but this should be able to be solved, and that would all of this would be very helpful. Okay, so I already talked about the fun prop like asymptotic intends to. So I think there should be something which can solve simple limits, which are like compositions of tag lemmas or asymptotics, but maybe in a higher generality than something like compute asymptotic, but you can't do harder problems. And then obviously long term, I think it would be nice if we have tactics for differentiation, integration, summation. And it would be helpful to have both convergence and calculation. I think differentiation is in progress in Silene. Probably you could do compute asymptotic could be made to do some of this in some cases, but not all cases. So obviously this is more of a long-term vision, but it would be nice eventually if you could do everything Wolfram Alpha could do, and it would be amazing if one day this lemma was just one tactic. I believe it might be many years, but that could certainly happen. Okay. Let's see. So I have 6 or 4 minutes left. So last I'm going to talk about so future work. So so the project, we finished a construction of Brownian motion. We proved some very basic API for them, but the project is still ongoing. And the next step is we want to prove a theorem called Ida's formula, which says that if x1 to xd are continuous semi-martingales, and f is a function from rd to r, which is twice continuously differentiable, then if we write x in this form, the process fx is a semi-martingale, and we have f of xt is equal to this. So you don't have to know what all that means, but basically this is like a fundamental theorem of calculus for stochastic calculus. So you can integrate with respect to a semi-martingale. In particular, you could choose Brownian motion. And this part here is like the fundamental theorem of calculus. But because of the fact that we talked about at the beginning, that Brownian motion is very erratic, in particular nowhere differentiable, that actually causes you to have this sort of extra term which pops up here in this formula, which has to do with sort of formally variation, but you could say informally the erratic behavior of the Brownian motion, or more generally semi-martingales. And this project will require developing the theory of continuous time martingales, defining the stochastic integral, and much more. And we're accepting new contributors. And Remy just posted actually in the Zulip that he wants to reinvigorate the project. So it's a great time to join up. I also wanted to maybe highlight two other sort of isolated projects that someone could take on, which I think, hopefully I'm not being too stating something that's too ambitious, but I think these would be good sort of one-off maybe master's projects, which build directly on this work. So one is Donskoy's theorem, which has that, so it's essentially like a functional CLT, and I stated a bit informally here, but it essentially says that if Sn is a sum of xi are just independent ID random variables, I should have written that, I didn't, and we sort of define this scaled version of the sum in this way, then the walk goes to BT. So one way to think of this is this sort of, at least qualitatively, not quantitatively, justifies the simulation I did at the beginning, because I simulated Brownian motion with a random walk, and this says that my random walk should converge in this scaling to Brownian motion. And then another nice result would be the law of iterated logarithms, which says that the lim sup of this goes to 1, lim inf of this goes to 1 almost surely. And what this sort of means is that if you drop a cone with the line square root 2 t log t and square root of 2t, negative square root t log t, if you draw these lines, then Brownian motion if you draw the graph of it, as you go to infinity, it'll sort of almost surely eventually never leave these two lines, but it'll sort of bounce back arbitrarily close to the top line and then down to the bottom line. Yeah, okay. So I think that is everything. Any questions?